So I'm here today with Peter Elder, who's the Chief Science Officer at the Canadian Nuclear Safety Commission. Thank you so much for taking the time.
Well, it's a pleasure to come talk to you.
Well, I'd love to learn all about this position that you've got here and kind of how you see the whole space. But as I force everyone to do, we're going to have to start from the beginning.
All right.
And where you first even found nuclear.
So I wouldn't say it was completely by accident. So I was going through university at the time. I was going through University of Toronto. They actually did have a kind of nuclear engineering program. There was an option off one of the programs. So I took some of the courses at that time and was sort of testing it out, and then decided, well,
you were like a mechanical engineer or something?
Mechanical, engineering. It was engineering science program, so you get the options. So there was actually a physics option, and so I steered towards the physics option, but added some nuclear engineering courses.
Cool.
And after that, decided, well, I'm not really sure what I was going to do, so I did a master's, and I did a master's actually in material science. So in not thinking nuclear, but did it on high temperature ceramics. And then when I was going through this one, someone said, well, nuclear fuel is a high temperature ceramic, UO2. And so I went, oh, never really thought of it that way. So I actually got a job at working at Chalk River at the laboratories there.
Yeah, good old Chalk River.
Yeah, good. So it was a combination. It was an interesting position because I was able to use both my physics side and the material side. Was doing working on combination. We were doing higher temperature fuel behavior, but we were also at the same time to do that, we were actually looking at fission product release. So using a lot of gamma spectrometry, so you learn very quickly around, it's kind of interesting when you're using in reactor fuel and that one, you realize there's a whole bunch of different isotopes that you only see in reactor that never exist outside the reactor, and how do you measure those and differentiate?
And when you talk about fission product release and maybe you can just kind of like piece this out for us. So you've got your, and you're dealing mostly with the ceramic uranium oxide?
Yep.
Okay, so you got uranium oxide fuel pellet. As the audience has probably heard 100 times, it's like the size of the tip of your finger, right? That's a good way to describe it. And then that is a ceramic. You probably know what a ceramic feels like, but it's heavy because it's got uranium in it and it's bound to oxygen. And the fission, the thing that creates heat and creates energy, is happening like an atom here, an atom there, kind of distributed throughout these little pellets, right? But the fission products, the thing that the uranium splits into, and it could be a whole host of different isotopes because it can split all different ways, they're kind of trapped there inside.
And so they're trapped. Yeah, they become trapped inside, and it depends on a lot of things. Like, so one of the things that we were looking at is that they trapped inside, but how do they move? Can they? So some of them are completely soluble in the uranium. So they just replace a uranium atom and it just goes on. Other ones, like especially if you produce a fair amount of xenon, xenon noble gases, insoluble. How do they, so they have to sit there, and do they create bubbles? What do they do?
Yeah, so what do they do?
So it really depends on the operating temperature of the fuel. And what you find is in light water reactor fuel, like common in the States, the operating center and the centerline temperature is a little lower, and they just sort of sit where they go. What you find in CANDU fuel is our centerline temperature is slightly higher.
What are we talking here? Like 1500?
Like 1500, 1600, which is just enough for these to migrate out of the pellet, and then they go into the gap of between the, they go into the space between the pellet and the sheath.
Fascinating, because So you're telling me that these like little tiny bubbles, these atom-sized bubbles, will like, what do they find each other and then create bigger ones, or do they all just kind of migrate out towards the side?
So they probably all migrate, and what you also find out is that the same thing will happen with iodines, and so one of the things they found and because of this changes and letting them back in CANDU fuel, they found initially when they were getting a lot of small defects in the sheath during operation. And there were various theories about what was going on and going back in. Turns out that what it was is that because of the operating temperature, some of the iodine was going into the sheath and was causing a stress corrosion cracking. So what they managed to do is they put a thin layer of carbon inside that acts as a iodine scavenger. So there's a lot of when you're looking at nuclear fuel there's a lot of complex processes going on because, as you said, of the fission. The composition of the fuel changes with time. Mm-hmm. So you start with its uranium oxide, but with time you produce plutonium. It sort of changes structure, so that some of that behavior changes with time as well. And it's important to understand that. Normally, when they go with this for normal operating conditions, you're just operating. It's fairly well understood. It's very stable. There are multiple all those barriers talk about from the, keeping the radioactivity in the fuel, the sheath, everything works. What a lot of the research is going on and said, well, what happens when you lose the coolant or one of those barriers breaks? And so we're looking so we're starting to understand and how to model this one. Like any science thing, you start with what are called single effect tests. So I'm going to take my uranium, and we are actually using this in hot cells. You take your uranium pellet and you heat it up in a furnace and see how the fission products come off. And then you get more complex ones when you say, well, wait a minute, there's actually a sheath there, so it has to go through the sheath. And it was trying to build that knowledge about, well, can they move? And more importantly, I think from a safety perspective, is how quickly they can come off and come back in. And what you find is that there are certain ones that can get released fairly easily, relatively easily. You still need quite high temperatures. But because there's so much sterile heat in the reactor, getting those high temperatures in accident conditions is relatively common, is that you can get a very quick sizable release of iodines and the cesiums, which is exactly what everybody models when they come out and looking at. So when you're looking at, trying to figure out the release fractions or things like this, or what can cause contamination, what you have to prevent against. There are generally two things you're always trying to prevent against to protect the public. One is, from a short term, it's iodines, and make sure because they short term, short half-life, go to your thyroid. So small amounts can be dangerous to humans. Then the other one is looking at the cesium, because cesium-137, it's a 30-year half-life. It will be, if it gets out, it's around for a very long time. Yeah. And that's what you're seeing at places like Chernobyl, where 30 years later, you still have quite measurable levels of cesium-137.
Now, maybe you can help me figure something out. This is something I've had in my mind for a long time. And we want to protect the public from, there's really, only a couple radionuclides that could hurt the public. The ones that are the medium-lived, right? Because the short-lived ones, they burn up too fast, even though they have a lot of energy, right. They're gone real fast. The long-lived ones, they're around for a really long time, but they're so low energy they can't hurt anyone. So you've only really got the middle ones that cause the threat. And then even amongst the middle ones, it's the ones that are like mobile in the environment, the ones that interact with human biology that we're really concerned about. And that's why we narrowed it down to those two, right?
That's as the surrogate of those two, is those are the ones that are most do exactly that. They interact with the environment, so you look at this one, you have some noble gases. Well, they're noble gases, they don't interact with anything, so they can be it's a pass through, but they won't stick into your body. Yeah. So what we're looking at the concern one, and the thing that's kind of fascinating on this one, out of those thousands of fission products and isotopes on that one, you come very quickly to saying there's only you can count them on one hand, the ones that you start to be really concerned about. And which means that when you're doing, when you're looking from a safety perspective, you can start to really focus on, okay, how do I capture these? So if you look at one of the common improvements post Fukushima was adding metallic filters. So these are passive filtering systems. And what are they trying to catch? They're trying to catch the iodine and cesium. So you can very focus on saying, no, I want to capture these two isotopes, these two elements, and these are what I'm focused on.
And how come that isn't the premise of nuclear safety? Instead of saying, hey, let's try to guarantee that we never have a meltdown, let's just say, let's assume, like a car crash, let's assume it's going to happen, and let's put a crumple zone, let's put an airbag, assuming it's going to happen. How come we don't do the same with the nuclear industry and say, instead of focusing so much on trying to make sure it never happens, let's put all of our effort into just these like metal filters around the core. So no matter what, we captured the cesium, we captured the iodine, job done. So
I guess when we look at it from a nuclear safety perspective, is we've always, in the simplistic world, is there are three things you need to do in a nuclear reactor. And so some of that has been there from the beginning, but one is control. So one of the things you need to be able to do is actually make sure you stopped the nuclear reaction in the reactor. Because if that's you got to look at it and saying, well, how can any system be defeated? So first thing you got to do, make sure you stopped it. And then you got to be able to cool it, because even if you have quite sophisticated systems, you're still going to make sure you want to be able to cool that so it doesn't continually releasing or cause another problem. Because actually, if you don't cool it, you can get the whole core can melt down, and that would cause some other issues. And the last one is containment. So that containment of keeping those those ones in compliant has always been there. So from the beginning. So we look at something like the filter venting is an addition to a containment system. So it's not a new system. But why you don't just put all your, one of the things.
Well, not put all your eggs in one basket. But what I'm saying is put the weighting on that. Let's build the most robust filtering systems that we can in the world, and put all of our technology and our innovation and our engineering dollars behind that, and lay off some of the other things, because the net effect will be greater or less hazard to human health. So
I guess you could look at it that way, but one of the things, the concepts that's been and that the safety uses is the defense in depth going back in. And and why you'd use that is because you generally find to say, well, I could just do this and everything. If that works, everything's fine. But then you always look and say, well, if that doesn't work? Mm-hmm. And the simplest solution is always stop the process the earliest you can, right? So everything's starting to go back in saying, no, I don't even want to go to that severe accident. Then I don't have to worry about what happens if my systems fail down the road, right? So you always look at it saying, yeah, you consider what happens if systems fail, but you make you build the robust system from the beginning.
Does anyone ever challenge the defense in depth theory? Because I look at it from my mechanical engineering background and not being in the whole nuclear world, and I'm calling, I actually think the defense in depth theory has some flaws in it. Because I think about it like this. A gigawatt scale nuclear plant and a gigawatt scale coal plant, essentially the same thing. A gigawatt scale nuclear plant costs $10 billion, where the coal plant costs $1 billion. There's $9 billion of safety systems in your bucket there. Now, if I were to look at say, okay, I've got $9 billion to spend on safety systems, I'm not just going to try to spread it all out evenly. I'm going to put a 50-foot thick steel wall and say, okay, according to the laws of physics, nothing's getting through this thing, job well done. But the defense in depth theory says you can't do that. The defense in depth theory says you have to, like, at each level, you got to stop the reaction.
So I guess you'd look at it, and maybe if you just solely from a safety perspective, you would say, I just make my containment the biggest I can, and then whatever happens inside, from a safety perspective, I really don't care. That's not a good operational position, because you actually, when you get a defense in depth, what you actually try to do is you try to say the best safety is for the machine to design as it was to operate normally. And therefore you don't, and that's also the most economic thing to happen. One of the things, and I know there is economics that always comes into nuclear, is that it's when you look at, you look at life cycle costs, and certainly because of the safety features, you are building safety in. But on the other side, saying the upfront capital is your most, that's most of your costs. The cost of the fuel is much smaller than it is, say, in a coal plant and things like that. And I guess going back in and saying, if you wanted to have the same level of regulation around coal plants about what they do to the environment, you would be spending a lot on your coal plants on scrubbers and capture systems to capture what comes off. But I think from the defense in depth developed because it was a combination of what needs to be done to operate the facility. And again, if you wanted to look at it from a designer perspective, you don't want to design where, I don't care how I operate it, I can melt it down and then nothing gets out. You still have a huge liability to the operator from having this meltdown and things like that.
But isn't that up to commercial economics to sort out themselves? From the regulator perspective, shouldn't it just be, as long as we protect the public, what you do inside your building doesn't matter?
You could look at it that way. I think the fallacy of looking at it that way is that you can actively predict exactly what's going to happen in all scenarios. And if you look at any actual accident, it's not, one thing failed. It's a multiple of small things happening leading up to a more major event. And the best way, and you can look at this in the matter what you look at it from a probabilistic point of view or a defense in depth, is saying if you come back in and saying, if I have multiple barriers, then the chances of those, that accident, and this comes back to what's used as a Swiss cheese model, where every barrier has a deficiency. And you only get an accident when all those holes in the Swiss cheese line up. And the idea is to have enough that the probability of them lining up is really small. And what you find is if you put too much emphasis on one barrier, no barrier is foolproof. So even if you had your really thick containment system and things like that, people at some point, people have to go in and out, wires have to go in and out. You can't build something that is actually completely airtight, completely that one, that that you would want to say from engineering, it's better to put all my things into one basket.
As a regulator, would you even accept a company coming to you and saying, hey, we want to test out a different theory other than defense in depth. We obviously don't want to sacrifice safety. Safety is our number one priority, but we want to test out something other than defense in depth. Would you guys give it its due diligence?
I think, I think some of these things are being questioned a bit by the small modular reactors to advanced reactor designs, where the concept is still there. The question would be how we have traditionally knowledge what those defense in depth barriers are. may not be relevant to a different design. When you go look at, and so you would still want to say, I don't want the radioactivity to get out of the building. In a classic light water, pressurized water design, what do? You build a containment. Why do you build a containment? Because you have a lot of energy in there, and you have a big driving force to get things out, which is all the pressurized water. Well, if you come back in and you have a liquid, a molten salt reactor that's operating at that it's not pressurized, then is containment what you need, or you need something else, right? To say, I need containment. What's going to push the falling back in? Maybe I need, in that case, it said, well, actually, I just need a core catcher or something to capture the molten salt if it leaks.
Yes.
And the chances of things going out are very small.
And then do you guys make that consideration, let's say for molten salts? Do you say mostly everything's going to stay in because there's less pressure? Yeah, some xenon gas will still escape, but we don't care about the xenon gas because it gets diluted in the atmosphere instantly?
Well, you'd still look at this and said, what can, we expect to go through and said, what could come out? And you have systems, and we've seen this in research reactors, where you say, I don't need containment. You have what's called a confinement system, where, there's a path out, but because it's low pressure, not that hot, you can use a sort of more normal venting, venting and filtering system. So you still have a venting and filtering system. It just would not necessarily say it has to be able to, deal with high pressures, large amounts of hydrogen, all these things that you're coming with the large reactors.
I'd love that though, but so this is what I've been thinking about with Fukushima specifically. Wouldn't they have been better off with confinement and a filter rather than containment, which traps the hydrogen gas and creates more of a path for mobility for radionuclides? Why don't light water reactors, gigawatt scale light water reactors, still abide by that same design principle, confine and filter, rather than contain and create a potentially hydrogen-filled environment?
So it is an interesting question, because what you would find, and everything reactor has it. There's been a knowing that the hydrogen production is there, is a possibility. Reactors have different ways to deal with it, and one of the things you look at there, though, is saying you still have, because you have the potential, again, it's saying, is that your hydrogen system fuel-proof that you can never have an explosion? And you can have different types of explosions, right? You can have a steam explosion, you can have a hydrogen explosion. So can you prevent, you can say, no, those aren't going to happen, so I don't need a robust containment to deal with that. And that's a very difficult when you're dealing with a very large heat source, a very large, you got to look at this gigawatt scale. There's a lot of energy stored in the system.
Yeah.
And I think that's why they're going back in. I think what may, and when we learned the immediate lessons from Fukushima about emergency response, about don't tolerate known deficiencies. Well, you deal with it now. Don't say, I'm going to shut down in a year so I can live with that risk. What we don't necessarily know yet is they had systems to deal with hydrogen. They had venting systems. And why did those not work as they were designed? And so I think, and that's where it's going to take, some more, forensic engineering to go back in and say, well, what happened in those ones? Was it the fact that while the safety systems all survived the earthquake, shut down the plant, was there some damage on some of these secondary mitigation systems that was not immediately available? So when they went to use them, they didn't work as properly. They all had a venting system. Everybody knew, and those designs had, I don't want hydrogen building up inside my building.
Yeah.
So they had venting systems to get it out. They clearly didn't work as they were designed.
So maybe there's some unexpected Swiss hole synergy that happens during 9.0 earthquakes that.
That's why, and this is a really interesting question that comes up to
the common cause failure.
Common cause, or where you put in and saying, what do you want to do? The first thing you always look at from, again, going back to those nuclear safety principles, is post-earthquake, the first thing everybody had been focusing on is, can I shut down the reactor?
Yeah.
And you want those systems to be really highly qualified and everything. And then, can I cool the reactor? They didn't think of, earthquakes come with tsunamis, right? So the real problem went into, you had pumps in the basement gets flooded, and you lose all your standby. You lose your power source for your pumps. But it's then walking through of what are the real, and this is where even any type of reactor is saying, really looking at what are the external hazards that can it face, and can you replace, deal with them. And I know with some of the advanced reactors, people are looking and said, well, if I build it underground, it's less likely to be affected by certain things.
Yeah. So what's the theory with that? Why not just put them all underground and say, all right, you got 50 feet of soil ahead of you, nothing's getting through that. No.
So that's some of the ones that the advanced reactors are looking at. I still don't know, and as a safety, we're a safety regulator. We don't look at economics. I don't know what the economics of building everything, instead of below grade looks like. But
from a safety perspective, does that look better?
It looks better.
Yeah.
Sure. You can have things, and not only from a safety perspective, security and things like that. And everything's harder to get at, less likely to, it's removed from an external hazard, even human-induced external hazard. If it's low. So some of those new reactors, and they're smaller, and because they're smaller size, they're able to look at these things as a possibility to actually build below grade.
Yeah, I asked Romina this before, but it seems to me that it would be a pretty straightforward argument to just say, okay, anywhere that we've drilled for a mine shaft or a or an oil well or something, just throw a small reactor in the bottom of that thing. It's below grade, nothing's getting out. It's already filled with toxic chemicals. So if there's any contamination down there, like we've already contaminated the water down there beyond what radionuclides could do. Like, why isn't that just a real quick, cheap, easy, it's totally safe solution? Just drop it a mile beneath ground.
It's there's always a question of saying, well, is it, and this comes back to the the length of time of the cost of the reactors. Is it designed to do that? What other risks are you putting in there? So when you come back in and saying there's a process, and why we go through the process is to say, well, let's. There's a tendency, and we see this with some of the new designs, is everybody's focusing on, I'm solving a known problem with large reactors. Without going, well, are you creating a new problem?
Right. And we had 50 years of experience with light water reactors to even figure out what those problems were. How could we possibly predict what corrosion issue is going to come up with?
But we did. I mean, while you say that, the experience has said, sure, we didn't get everything, at the beginning. But when you go back to the beginning of how they looked at the large reactors, most of the risks were properly identified.
Right.
Okay. But the time in history has said, well, some of them going back to defense and death, you could use has said, well, when you look at a probabilistic tool, some of these ones, sure, it could happen, but it then comes, well, it's very, very unlikely to happen. And are you putting a lot of effort into protecting against something that is very unlikely to happen, and actually making something else more likely?
Right, like the big loca versus the small loca.
The big locus versus small loca is the classic on that one. Is that you put this one, but in terms of what could go wrong, it was, sort of the simplistic. Well, it was simplistic, but when starting from you didn't know and said, what happens if the biggest pipe in the plant breaks?
Yeah.
Right? And one of the things, we would look at when you're looking at SMRs, the designers should take that sort of, or the safety analysts should take the same philosophy. So what happens if that breaks? And it may come because of the circumstances, the fuel design, the pressure and everything. You'll get the not much answer. But then you've looked at it and then you can move through. But it's important for us when we're talking to designers that they think about these things and saying, okay, yes, you've eliminated that one, but have you reduced anything else?
And what about the ones that even as the regulator, that you can't anticipate, but it's still your job to protect? For instance, like the Davis-Besse thing, you remember where it's like the steam, there's a tiny little steam leak, but so that you had like the acid would like form on the edge and then it eventually ate through like over time. Like they couldn't have predicted that ahead of time.
They couldn't have, and this is where we said what we again is what we've learned in those 50 years of regulation is much less on the physical side. There are things you can't predict, but there's much on saying what happens a large break. What we've noticed is saying, well, if you have things, importance of safety culture, maintenance, of questioning attitudes, because when you say you couldn't predict exactly what was going to happen at Davis-Besse, when you look back, there were signs that they had lost control of their acid. There were acid problems all over the plant.
Right.
So someone wasn't questioning, why is that corroding? Why am I seeing this? And it was in a situation where, and going back in, so one of the things that I thought was always interesting about Davis-Besse was it took about a year to replace the head. It took 2 years to convince the regulator that they fixed their internal processes.
Right.
And that's really going back in the importance of those internal processes, the importance of preventing, making sure that you have preventive maintenance, that you are looking at things and not just saying, yeah, I think it's okay, versus, no, I want to make sure this is okay. Because what you find is that sort of thing also has a win on the economics of the plants as well.
But one of the things that I'm really more concerned about is that, so new reactor designers, they're going to bring new fuel cycles, new chemistry stuff that we've never seen before. Yes, there's the things that we know about the light water reactors, we like the thing you just said, we know you need good operational practices. We feel confident in that. Yeah. But there's always the thing that you don't know what you don't know. And I guess my fear isn't that a bad thing is going to happen, because if it's small enough, and like I said, if it's underground or something, I'm just not worried about it from a safety perspective. But I'm afraid that the regulators might not have the confidence to ever sign off on a completely new set of chemistries that they've never seen before, because they don't want it to, because if something does go bad, they don't want their signature to be on the piece of paper.
I don't think, and that's always interesting about how you approach, innovation. And what we're finding, and we've done this, we're doing these vendor design reviews on these SMRs. And
how's it going?
They're going all right, in terms of, but we are both, the vendor learns and we learn. And I think that's an important process to go through. And so one of the things you're finding is that in often cases, you have to go back to those basic safety principles. What are we trying to do? What are we trying to protect? Rather than saying, oh, this is how I normally assess this, and going, well, that doesn't make, you find, my rules don't make, my detailed rules of how you apply those principles don't make sense. But the principles always apply. And the other one, and this has both value from, to the vendors and to the regulators, is that no one comes out and said, I want to produce this I'm just going to design my reactor and build it and it's going to be fine. There's always a process of looking at, do you build a prototype, do you build a demonstration reactor? And when you have that sort of approach, there are ways to give the regulator more confidence or deal with there's uncertainty here. So can we help deal with that uncertainty by having an extra protection system that we may not have on the next one, but in this case we're going to put this in. And one of the big things you find is that when you do a demonstration, you're not trying to run it at full power for a very long time, right? You're willing to that one, so you look at that one. You're willing to do more inspections. You're willing to do more, and you may add, and going back in saying, and both everywhere I've seen, they're building on existing reactor sites, so they come with or existing nuclear facility sites. So you come with a very high level of emergency planning. You come with a very high level of security. Do you need those for the long term? Maybe, maybe not, or probably not at that level. You can say that one. But you're also then giving the regulator said, okay, I'm compensating for, I've got some uncertainties. Here's my compensation for those uncertainties.
But if you go to the regulator and you say, okay, so I've got some uncertainties, here's something I'm going to do to compensate it, it's going to make it safer. Why would the regulator ever let you take that back and say we want to make it less safe now? Isn't more safe always better? And you company just proved to us you know a way to make it safer. You told us it's more safe. Why would we ever let you make a plant that's less safe than you proved to us that you can do?
And that comes back into saying these are compensating measures because you've got uncertainties, and I think if you approach it that way, and it is actually how you looked at these systems in the past. You said yes, the regulator are always going about, well, why don't you continue to do that? And it's then when you get what advantage of actually having real operating experience, real data, is then the operators, the vendors are allowed and will bring in, well, now I have actual real data, look at my probabilities of failure and saying, I don't need this one because it's not really adding a safety benefit, whenever you're going back in. And those arguments, and regulators have accepted those arguments with time. Right, so you can't. It's just going back in. It's very hard to start from the beginning. But I think with time you'll see that people will come in and say, yeah, that doesn't make sense. And there's also when they look at this one, when you have actual data from operating experience, it's not only the costs in terms of money, but then saying, well, I'm doing all these extra inspections. How much are it costing in terms of dose to workers and things like that, right? So you can do cost benefit in a different way, and it's not just the cost of actual. We also look at it saying in terms of, well, what's the cost in terms of dose of these procedures? Am I getting a value? So they're balancing risks as well.
I like that. I really like that one. But I think one of the big handicaps the nuclear industry has is they can never use the safety argument outside of the box that we created for nuclear. We can't say, listen, we're making people safer by putting coal plants out of business. Like, look at the net effect that we're having on coal. No matter what we do, even if we had a Chernobyl a week, it'd be better than coal. We can't use that argument for safety.
No, and I think that will never, it's human nature. Like the airline argument, airlines can't use that argument either. All the stats say it's safer to fly around than to drive, but they don't.
But the Drug Administration does. The FDA, at least in the U.S., they are allowed to use that. They're allowed to say this drug, 10% of people have an allergic reaction to. If you come out and even if you're killing, 9,000 babies a year, but it was less than the 10% of the previous drug that we had on the market, you're allowed to put that drug out of business, even if you're killing 9,000 babies. Why does that work in the drug industry and not the power industry?
It's interesting. There are interesting questions, and how much of that is both how you approach it, but I think it also depends on how the power industry is regulated, and that and the role in both Canada and the United States. So there are provinces and states that have a role in that in making certain questions. So if you look at it from a Canadian perspective for our perspective as a national regulator, that choice between building a coal-fired plant and a nuclear plant is a provincial choice. Once they've made that choice, our job is to make sure it's done safely on the nuclear side. Yeah. But one of the things that you're saying they can't make these arguments. One of the things that's coming up is that the government just passed a new legislation on impact assessment. So replacing environmental assessment as an impact assessment. And that impact assessment is actually allowed to do both negative and positive impacts. So a proponent could say, I'm putting this plan is to put this coal-fired plant out of place. And they can actually make the argument, not to a nuclear regulator, but generally to the a wider societal, when you're looking at impact assessment, they can actually make those arguments.
I love that. That's a Canadian thing?
Yeah, that's, and it's brand new. It's not enforced yet, but it does have the possibility of you saying, looking at the trade-offs, looking at the benefits, so that the impact's both positive and negative, and have a process to say, because the whole back end is saying that you want to make a structured decision. That doesn't affect how we do our core nuclear regulation. It's just a non-arm, but from a general societal view, there are some steps forward to try to at least make sure that you're having that dialogue.
You've been answering some of my toughest questions, so we're going to get into waste, where I've got a few more for you. Okay. I know that you're a specialist on the geological waste side of things too.
Well, I'm not a specialist, but I have dabbled in it enough to, and talk to our specialists along the way, but yeah.
So what's the current state?
The current state in Canada or general?
In general, how we think about this.
So how I think this, and as a chief scientist, this is always an interesting point of view, is that there has been a scientific consensus for a very long time, 20, 30 years, that a deep geological repository is the appropriate solution for nuclear waste. There are some other options going back in, but anything, even if you did reprocessing, you're still going to have some waste that you're going to have to manage in a very long time.
Can I push another one at you?
Sure.
This is what I'd like to hear from the scientific community, why this wasn't the ultimate solution. Dilution. Every other toxic chemical on the planet we dispose of through dilution. Dilution is the solution to pollution.
So that's an interesting point of view. I don't know if anybody really looked at that one, but it comes back to just going through the chemistry of that one and saying actually uranium's kind of, it is everywhere. The question is, how will you do it in a way that, how it moves in the environment, how it works, how the stability of it. It was always, and then there was always an ongoing debate about, is this waste?
Right.
Right.
That's it. That's what I was going to throw.
Or back in, and to the extent of there's a international convention. It's called the Joint Convention on Waste Management and Management, and spent fuel management of spent fuel.
Yeah.
Why it's joined is because some countries are going back in and said, well, spent fuel isn't necessarily waste.
Right.
But what we want to look at it and swing back in, the sort of scientific thing said, listen. The best thing to do is to mimic nature, isolate it for a very long period of time. It is feasible. We look at, and one thing back in, what has been the failure, I think, on this one and some other ones is that communicating to the public that this isn't just I'm just going to bury it in the backyard and forget about it, right? That it is actually a scientifically sound solution, and that you would monitor, and at some point it's going to be really expensive to go get it back, but not impossible.
And let me push this a little bit further, though. Can you describe to me the mechanism by which waste poses a hazard to human health?
So this comes back in terms of if you looked at it from so we were talking before about post accidents. You're worried about the those iodine and then the cesium. Cesium's your dominant concern for about the first 500 years. Okay. And it's a very mobile in the environment. It's high energy gamma ray. Small amounts can be quite hazardous, and there are fairly large amounts of nuclear fuel. After that, what you find would be driving the doses are then very small amounts of other things. So,
but what I actually meant was what is the predicted thesis by which you have something in a concrete cask, and even if you just kind of put it 10 feet underground, what is the predicted thesis by which humans would ever come into contact with the harmful substance?
So over time, and we know concrete does degrade.
Right, but as things degrade over time, they also dilute things slow enough over time such that they're not in a concentration where it can pose a hazard to human health. Like erosion is a very good way to very slowly spread something out in proportions that aren't hazardous.
You could look at that as going back in. It's just saying it's then looking at the concentration of what's in the material, right? So while you could look at this one saying there's still concentrated, this goes back to the maybe the side about you're getting a lot of power from that that little pellet. Well, it means that it also then comes with a fairly heavy concentration of fission products and things in that one. So that if you just sit it there, it's much more concentrated than some of the other areas we went back in you would see.
Right, but then isn't that counter to our thesis of we lump it all together, we put it all in one place, we're making it more concentrated? Whereas if we spread it out, and the other thing is, it's just like I've heard the back and forth on this, but I've never heard anyone describe to me a way that a human could be hurt, a realistic way that humans could be hurt by nuclear waste, spent fuel, whatever you want to call it, ever, like a realistic way if you just spread it out and dumped it in the ocean. Because like the other thing is like, okay, so let's say you don't like iodine 131 or iodine 129. Fine, the minute that it comes into contact with other iodine, it's self-protecting in the sense because elements might bioaccumulate, but isotopes biodivert, so it's like, you see what I'm saying?
Yeah, it's
like where's the document that says here's what we're afraid is going to happen to a human being from nuclear waste if we just diluted it?
Because I don't. That's a question. I don't know if it's been asked.
That's what I'm afraid.
No. But because there was a sense that the sort of I'm just going to dilute everything.
Like every chemical industry.
Every chemical is going, and that's how it's going back in. There are lots of examples from other industries that doesn't actually work as well as you think it could be done. There have been, and I think there was other going back in and said, well, we've actually, because if we collect it all, and that's different than the coal industry and some of the other ones where part of your pollution goes out right away. The nuclear has advantages, all collect it. That maybe we should try to deal with it rather than. So I don't think anybody really looked at that. But if you look at some of the other ones, and there's still some really tragic examples in Canada about mercury poisonings in streams and that, and you look and said, well, it worked. Dilution could work. I went back in and said it's never. At some point, yes, sure, there is always going to be some dilution you're taking credit for, but you can never rely completely on dilution.
Except with nuclear because of the quantities involved, right? Because like we could run the calculations on mercury, and the reason that mercury gets into the fish and we don't like that, is because of the quantities of mercury that have been released into the environment through human action.
Right.
It's just a mind-boggling amounts of mercury, okay? But we could also run the calculation, say, if we were to do the next 100,000 years on nuclear energy alone, and we were to dilute all that, it would be one millionth the amount of mercury that's in the ocean. And I would be okay with one millionth the amount of mercury in the ocean. I wouldn't be afraid of that.
Yeah, I guess it depends on how you look at it. And it's a my own comment on that one is that even when we've got a general science and consensus, getting a public consensus has been really difficult on something that is very silently sound on the deep geological repositories. I think some of these other solutions would be extreme, even impossible to get the general public to be able to accept. And that's where you've we've identified this risk. We're managing the risks. I think there are ways to legitimately manage it. I think to go back and say, well, actually, it wasn't as big as we thought is not a very realistic approach to how you'd solve the problem.
You're right. I feel like we've gotten ourselves in a real catch-22 here, because what I've learned, so I've also interviewed a bunch of psychologists and sociologists on the show as well. And one of the things I've learned is that we created the public fear of nuclear waste by categorizing it as something special that needs to be taken care of for a million years and buried and isolated. So we created that fear. But now if we went back and we said, okay, we're just going to dump it in the ocean, there'd be hell to pay, because people would be like, oh, it's just that industry getting away with more pollution or something. So it's almost like we're stuck in this log jam.
Well, I kind of look at it, and we've seen it as from a regulator as another point of view is it because we've identified it and the regulators have identified in management, it's only the industry that then is in position to say, well, actually, I know what my costs are. I know what my full life cycle costs are. Yeah. I understand this. The other one is to, so you're in the, I already come back in and saying, I think what we're doing is the appropriate thing to do. And going back in and saying, well, gee, other industries aren't doing it, doesn't mean that it necessarily isn't the appropriate thing to do.
And you're saying that within the box of we are just the nuclear industry, because one of the things that honestly keeps me up at night sometimes is just thinking that every cost that we add to nuclear, no matter how much we're protecting people from nuclear, what we've really done is we poison them with coal. By making it the cost comparison for these more dangerous energy sources, like, we're responsible for the coal deaths also, because we made nuclear more expensive. Maybe not when viewed inside the box.
Maybe, and I guess, and this is one of the point, and one of the sort of basic principles of nuclear regulation. You can have that argument with general policy people and things like that, but from regulatory position, you can't tie yourselves in knots by thinking about, well, what are the wider considerations, and that comes back to a regulator said someone has decided to use this power. They've made this choice versus other ones. Now our job is to make sure it's done safely.
Yeah,
and we don't look into those relative things like that. Which isn't to say that maybe there aren't some interesting studies that could do this one, but certainly from a regulatory position, it comes back to the basic of, no, we need to make sure that the choice is made. How do you make sure it's done safely?
Yeah. Good answer. Boy, you are on it. Okay, so I've harassed you with all my challenges now. What are some of the other topics that you wanted to cover?
Oh, one of the things I did want to discuss, because I think this is a topic where regulators do have some work to do, is this connection between nuclear safety and nuclear security. And traditionally, they were complete silos, and so that the engineers who ran the plant, okay, they're guys with guards out there, and they have weapons, and they'll prevent the bad guys coming in, and I don't really have to worry too much about them. What we're finding, one easy in that one isn't the best thing. There are some synergies, and and when you get into certain scenarios, you realize that what what would be a vulnerability to the plant from a security station. Most often, the safety guys had already thought about it, and they'd be slightly different. But I think what's coming, with the heightened importance of cybersecurity, is that the need for that there will be going to a point where there is no difference between safety and security. And one of the debates I know that's had internationally was called cybersecurity. And like, yes, but it causes safety problems, right? The purpose is to cause a safety problem. So you really have to look at it as a dual thing on use of that one. And it requires, and why, because of that, is that it requires a different approach to how you do basic engineering on inside a plant, and that you can't just say, well, I'm just looking at safety and someone else looks at security. The things that people don't think about, I need to replace a valve, and the valve comes and it's got a controller on it. Controller has Wi-Fi, because that's what things, Internet of Things, it comes on Wi-Fi. And the engineer who's specifying it for his valve doesn't really care it has Wi-Fi, right? It's not really in his view, but he should, because suddenly he's actually accidentally introduced a potential vulnerability in the plant, which means that doesn't mean that you can't counter it, but someone who looks over the cyber threats needs to understand that I've got this extra piece of equipment that has a Wi-Fi connection. And that becomes that then you have plans of how you manage those vulnerabilities.
Did you guys in the U.S. we found introducing digital controls to be too cost prohibitive from a regulatory approval standpoint? Do you guys have digital controls in Canadian plants?
We do have digital controls, and one of the you touched on an interesting point about regulators and about innovation, and that maybe all going back in, because digital controls is exactly that. But I'll explain the history in Canada. The industry first proposed a digital control for one of the safety computers in Darlington, which was being built in the mid '80s. And so we got some, we can, you look at this one and got some familiarity with it. And then said, we can actually see how this work, how you do this one. And because of that, as they went to more and more digital controllers, we had a comfort level of that. When you find some of the other regulators who nothing was really built from the analog age to when they came back in, everything was digital. They have no comfort level in how digital things necessarily work on that one. And it's really just saying, is that, convincing the regulators, is the regulator looking and saying, willing to say, is this a risk, or is this a risk that I'm not familiar with? And one of the things that I've always talked to my staff and saying, you have to look at it from, sure, you always want to concentrate on that risk of the new. What you have to do is then compare it to the risk of the current. And is it similar, or is it just, it's a different risk, but it's a similar level of risk. So when you're looking at controllers, on one hand, you're looking at, well, you have a choice of obsolescence or modern equipment. But also from a safety factor is that the digital controllers give you a lot more data. So that you get better at, the industry is going to get better at preventive maintenance and things like that one, because they have that digital
higher
data,
fidelity,
hiring them back in. And I think this is the area where the nuclear industry, certainly on the digital, needs to go out and learn from the aircraft industry, especially. Where they went from, and it's not talking about, and we will try to learn from what's happening with Boeing right now.
No, you don't even bring it up.
But that's not really the other end. It's more interesting in saying, looking at how did they get to accepting the whole fly-by-wire planes, so that they went from going back in where the pilot, when he pulled something, he was mechanically moving something, and there were a whole bunch of cables and that, to now It's all done by computer.
Yeah, how did they accept that? Because to me, it's like there's nothing that can stop hackers at large, right? Because even Microsoft, it's got thousands of the best computer scientists that ever existed working there. Same with IBM. They can't even stop the hackers. How did the airline industry figure out how to stop the hackers?
I think and this is one of the advantages I think we see within some nuclear plants is that you can isolate, right? You're not going back in, and they also went to a very, very high degree of redundancy. When you come in and say, my computer fails, I can't fly this plane. Well, you better have a backup for your backups.
Okay.
And what you're finding, the quick ones on the 737 MAX is that they lost some of those principles when they were adapting this to older technology.
Yeah.
Like, from fully digital, you go and said, I need a high degree of redundancy, right, to get that. And they knew, and the industry also knew that they had to have a very high, high reliability. Well, then you need a high level of redundancy if you're doing digital systems. And generally, they seem to have done a very good job on that on the fully digital planes. So the question would be, well, there's a way to do that with a power plant too, I think. And I don't think we can go forward assuming that you're not going to use digital systems and heavily redundant, heavily relying on digital systems. It's then saying, how do we get high reliability of my digital systems?
Peter, as we wrap up here, maybe you can just leave us with, looking forward into the future, what you see coming down the line. What do you predict the nuclear world's going to look like 10 years from now?
That is a really tough, question right now, because it really looking at back in of saying, and I guess it's more of it's not really a safety question around the SMRs, but can they make that sort of social economic case to make people say, yeah, we've got to go this way. And that is a real potential to be, a very different question, is to say, is it, as you were saying before, do we have decided as a society that, yeah, climate change is so important that I'm, as a society willing to accept or address some of my fears around nuclear. I think, you will see some progress on that one as we go forward, is that, you will see some of these small reactors being deployed. You will still see the big reactors, continue. I don't know if there'll be too much of building of new ones, but certainly that life extension trial thing will continue to be, because that gives you that stark comparison. So I close this down, what am I replacing it with? And then you can say, okay, I know exactly what I'm replacing it with. It's going to be natural gas or coal or things like that. That, I think as you're going forward, you got the point where coal isn't terribly socially acceptable. I think the next one will be natural gas, and burning natural gas for electricity will be, no, that's not something that becomes socially acceptable. Doesn't mean it gets outlawed, but it's saying, no, that's what the general sense is. And that will put a lot of pressure on making sure that we have enough electricity, and you're going to have to look at all the sources of electricity moving forward.
Peter Elder, thank you so much.
Okay, thank you.